So thank you everyone for attending this second international symposium on the application of AI in metallurgy and material engineering. In particular, I want to thank Harry Badashia and has kindly agreed to talk, and our Provost Chancellor Paul Monks and agreed to chair to say introductory words for this seminar. This is today's agenda. And we'll start with Paul, and then I'll give a short talk to warm up for Harry's keynote, and followed by short discussions in the end. Right. So now I'll pass this to you, Paul. All right. Paul Monks is a professor of atmospheric chemistry and Earth observation, and Provost Chancellor and head of College of Science and Engineering. And he will be the Chief Scientific Advisor for the Department of Business, Energy, and Industry Strategy. Paul.
Okay, thank you very much, Hong, for those kind words, and hopefully you can all hear me and I haven't fallen for the great mute trap of Zoom. It's my pleasure to introduce this symposium this afternoon. I believe, and I'm informed, that it really follows on from the success of the first international forum on the application of artificial intelligence in metallurgical and materials engineering, which was held at the University of Science and Technology in Beijing in August in 2019. The reason we find ourselves online today is probably not particularly unusual. It's part of the COVID crisis. There was a second symposium planned for this summer to be hosted by the University of Leicester. So the organising committee took the decision to move the conference online and arrange a series of weekly webinars for the 4 consecutive weeks to cover most of the up-to-date AI research in relation to metallurgy and materials. I mean, the aim of this conference is to disseminate the latest research activities in the application of artificial intelligence and/or data-driven approaches to materials design and process optimization for metallic materials, with the goal ultimately to accelerate the development of intelligent manufacturing technology in the materials and metallurgical industry, and to provide an international platform for discussion by scientists, engineers, technologists, and industry leaders. I think I'm more than fully aware that really the application of artificial intelligence in metallurgy and materials really has the ability to enhance the quality of materials, improve process efficiency, reliability and safety, as well as conserving energy, reducing CO2 emissions in manufacturing. And really, it could encompass all of the latest manufacturing systems, intelligence devices, inter-machine communication, and data analysis. I mean, I just want to, having given that formal introduction, is recognize what an important area this is. As part of my role as head of college, I've had the pleasure of going to various steelworks around the world and understanding the challenges of metallurgy and materials engineering. And I've seen the power that AI can bring, but also the challenges that AI also brings in order to do this. I'm more than aware it's not a panacea to all ills. I think one of the things that I've learned just starting my new role and beginning to start getting into my new role in BEIS is the real big push towards a zero carbon future, a low carbon future. And I think that much materials and metallurgy, and it's great to hear this seminar, really begin to grasp the issues around AI and how that can be used to drive, let's not pretend it's a total greening of these processes, but at least the reduction of significant greenhouse gas emissions from things such as the metallurgy and materials processes. So thank you very much for inviting me to introduce this seminar, and I hope it goes really well today, and I look forward to hearing the outputs in the coming periods of time. So thank you very much indeed. Over to you, Hong, to give your short talk.
Thank you, Paul, and then for give us this very broad view on this application of AI in steel industry. I wish, and then we will have more funding on the steel from the BEIS in the future. Right?
Always worth a try, Hong. Always worth a try.
Yeah. Let me see. Right. Now I'll move on to my short talk on metallurgy and process sciences for application of AI in steel manufacturing. I'm professor of materials engineering at the University of Leicester. I also would like to thank the Royal Academy of Engineering, and then and also for the EPSRC and LISCO for sponsoring my research work in the past. So we first start with steel. Why steel is important? We say a healthy economy needs a healthy steel industry. Steel is the backbone of material and in modern societies, and it covers probably every sector you will imagine, start from cars, trains, or airplanes, right? It is one of very few material to be infinitively and easily recyclable without loss of quality. And this is one of the key actually aspects of the steel, and we can recycle, reuse it. And in the last year, 2019, and the world produced 1.87 billion tons of steel, which consuming about 1.07 billion tons of coal, equivalent of energy, and also produced or yielding 3.17 billion tons of CO2, and which accounts for approximately 6.7% of total world CO2 emissions. The steel industry ranks as the second major energy consumer and the largest emitter of CO2 in the world industry sector. As Paul mentioned, the CO2 and environment protection will be one of the future direction for the steel industry, right? And then the demand for steel and globally and is expected probably to be doubled by the year 2050. So making steel is a process, and it's a long process. And the top one is actually it's a view of a steel factory plants. If large actual steel factory could be like more than a size of town and a small city like. The process starts from raw materials, and you need to have coal, which provides the carbon and also provides energy to the steel iron making process, and with ore. And you have process of coking and sintering and petrolizing, and then for making irons, and then followed by steel making and continue casting, rolling, and to the final products. So it is very complex, which is a process. And if you look at these variables in the steel making process, and you probably count more than 4,000 variables, and with probably 50 of them are the key variables in this steel making process, right? So we need to have some key insight and to enable probably real-time guidance to deliver solution to start from iron making to steel making to the final products, to essentially to build a digital platform and to enable this real-time guidance. So that's the process side. If you look at the material side, or property side, and this is one example, and we developed in one of the EU project. And then we look at multi-scale, multi-physical kind of aspects of metal processing. One thing I want to emphasize, those data in the metal alloys is also very complex, and also is high dimensional. You can start from very small scales for electron interaction, and to molecular scale, look at atomic probably interaction to phases, which is micro scale, and which will be key actually for steel, because many of mechanical properties are determined by the microstructure and also defects at this scale. But you look at the processing side, goes down to the grain structures, and to the macro side, looking to processing variables. So if you look at this diagram, we start from top one will be determined materials, and bottom one is processing, and right hand side one, it is performance. To correlate them, it is very challenging, and then we have been trying very hard to what we call multi-scale, multi-physics simulation, but passing the data or identifying the data are difficult. So those are the challenges for us to do it. So process-wise, and you will have hundreds of thousands sensors, scanners, detectors, and use it every day in steel industry or in materials laboratories. And materials-wise, and we have immense amount of knowledge and insight it contains. So how to use those process science and materials and metallurgy, and to make those make use of them and to produce quality steel in a smarter, faster, and more precise way, right? And you may think this is kind of wish list, but this is the things. And then see, with the available supercomputing and available big data, we may have a chance to look at it in a different way, in a smarter, faster, and more precise ways. One of the example, which is very recent one, is called Big River Steel in States. It started in July 2014 and then operated in March 2016. And this is, the claim is world first intelligent steel plant in the world. Their slogan is, we are a high-tech company, happens to make steel, right? So every year they plan to make 1.65 million tons, and they only have 435 employees, and which probably equals to about 5,000 tons per capita. And this is big improve. And if you look at the rest of the world, probably normally will produce 1,000 tons per capita. That would be probably a typical value for these modern steel plants. By collaborating with AI company and the combined planning, scheduling, marketing, and together with processing and metallurgical science, and to make this kind of fully digital steel plants and in operation. So they have AI system connects every part of complex steel manufacturing process to find optimal solution that is integrated to a level which was previously thought impossible. Every point of steel making process from the furnace to the shipping bay now can be analyzed and optimized for the maximum quality and productivity. By using this predictive data capacity, and steel making now can be at the highest level of accuracy and efficiency. So if you look inside the systems, and then you can start from top level would be decision making, followed by probably intelligent management, looking at virtual realities, and then down to the more kind of a quality performance side to digital production, followed by this, we said, correlation between chemistry, processing, and performance. So at this management level, so they have intelligent production scheduling. For example, they used to operate in the furnace, electric arc furnace, according to electricity price. And also they can predict, actually use big data, predict the market and the demand, and to planning for the production. And also they can have factory assets, has monitoring system, and to predict lifing of each component of each component in the steel factory. Actually, this will financially gain significantly. Again, at factory level, they will have digital twinning. Essentially, they're probably online monitoring every parts of each processes. So those mainly are those knowledge mainly are management, scheduling, planning, or automation. But where is materials or metallurgy science come into play, and how could we contribute to this kind of a digital development in the steel industry? Right. So this is the thing we said, probably we want to probably move on from a previous kind of physics-based modeling to data-driven modeling, and try to correlate the chemistry processing and the properties. Essentially, this is material science, to correlate between chemistry, processing variables, and properties. So this would be probably the topic I will follow on. You might talk. So challenges, right, for us. And then the first one is data connection or data mining. And we may not have the data we want. So we probably need kind of capital investment to look into inform the value of information, right? Look into new sensor simulation and experiment, because this needs to be identified and where to invest. And then probably you will find probably data is not enough. And then to mitigate this, and we need to bring the simulation on board. So, and then to integrate the production data or re-experimental data with simulation data together. Right? I will give you one example later on and how actually the way to integrate the production data with simulation outputs. And definitely you have big data in industry, you have big data, but how to analyze them, and they're quite different with academic users, okay? And also they are complex and they're nonlinear. So, and then we probably need AI to help us to analyzing those data, to correlate those data. So following on, and then said we start from process monitoring. The real application which industry can benefit is to move on from online monitoring to online control and final decision making. If we want to move on from online monitoring to online control, and we need to be able to have rapid prediction of current and future process status. As a material scientist, because previously when we use the physics-based modeling, and then it takes time, it takes weeks or it takes months to do a large-scale simulation. But from now on, we need to get fast simulation, to develop fast simulation method using data approach, and based on the current state to predict what happened in the future or what happened in the next or downstream processes. So that I mentioned earlier, those data from industrial is huge. If you do variables, and then can be 4,000 or at least 50,000 input variables, and the final product will be your quality of products or efficiency of production. But those data is bigger, and then it's complex, and then probably don't know where you are actually in this multi-dimensional space. And as shown in those diagrams, if it's in a one dimension, one-to-one, you can develop linear or parabola kind of correlations. And if it's three-dimensional, you still be able to figure them out. And you got 50 or 40 or input variables, and then would be impossible and to correlate them without probably using of AI, right? So there is really need for us to move on from physics-based modeling to data-driven ones. So, and then AI essentially, you say mathematicians or control or computer scientists, they should be able to implement or develop AI. We call it legacy AI, but as a material scientist, and what's our role to do it, right? Our role probably, as shown in this diagram, we are probably act as a corrector, right? And to ensure this output and could be interpreted in a right way, and then to make the right decision or modify the decision and to reduce the risks. So this dovetails, other material scientists or metallurgists, and we probably need to work together with the top layer of kind of intelligence system, from management to the automation system, and to provide a real correlation about chemistry, processing, and properties. So in this webinar, we have serious webinars, and we arrange a couple of talks each week to look into data-driven modeling approach to correlate chemistry, processing, and variables and properties. And today, and so Harry Badashi will give a keynote on empiric learning in material science. And next week, we have a computation, the material science for metal additive manufacturing, from fluid dynamics to digital material science design. It's given by Dr. Shinapat Panwiswas from Leicester. And then Richard Curry from Swansea University will talk about digital manufacturing with the Sustain Future Manufacturing Hub. Sustain is a UK a consortium looking to sustainable development in steel industry. And then we will have a Professor Jin Yang from Shanghai University to talk about the development of artificial intelligence, metallurgy technology based on big data. And then Inzu Enit will talk about, from Oxford, will talk about study of nucleation in aluminum alloys, followed by Dr. Vic Castino and from Lawrence Livermore National Laboratory. And he will talk about a method he developed looking to fast running method empowers the plant manager by providing the best real-time prediction possible. And also we have Professor Yi Ke Guo. He was actually the director of London Big Data Center. Now he taking up this Provost Chancellor in Hong Kong Baptist University, and he will talk on big data. And there are many more to come. Probably I'll use a couple of minutes just to show us what we have done in Leicester, right? So we have fundamental study at Leicester. We're developing fast-running simulation methods for manufacturing use deep learning, right? And we have a few case studies, it's ongoing case studies, looking at process optimization, looking at mechanic property prediction, using industrial data, and then use AI to predict defects, certification correction, which is following actually Harry did work 20 years ago. Actually, work we started further using deep learning method, and also look into a new program or new kind of automatic recalculation of certification structure algorithm. Also developed in my team, and then how to generate big data for single crystal alloys. We are actually working with Rolls-Royce, and this will be taken forward by them, right? And then look for AI for alloy design and a knowledge-based digital platform, and which we are a member of the large consortium called Welding Galaxy. So we'll start with this with a process kind of optimization program. Essentially, we want to develop fast-running process and simulation method, which can enable the industry and then move on from online monitoring to online control. Right. This is a simple case study, and it was using this glass forming technology. But in principle, we say in glass forming, they also control temperature, the control flow, and the control chemistry. They are much in common of steel making, but it's much simpler case study. And we defined what are inputs and what can be changed. So this probably it's a schematic diagram of what in collaboration with Wika, we are working together to see how this can be has been done, right? For example, in this one, we will have probably 8 input channels, and then look into temperature, pressure, velocity, chemistry, and so on. So in each of these variables, and you can do this kind of matrix kind of simulation, right? And again, those simulation will be validated against some key experiments, and which has been measured in industry. So you need to ensure the simulation at each grid point has been validated, right? And then you will have those simulation results, and will be saved into data format. And then work with online monitoring system. For example, at this time, you got a set of variable, and we're sitting within this range from this 7 or 8 input range. And then you use this kind of AI and to quickly to predict what can happen, for example, in next time step of the same domain, or what will happen in the downstream process. we said the fast run method. This will empower the plant manager by providing the best real-time prediction. Right. By doing so, actually, we tried to implement in a medium-sized glass forming industry, and again, probably $1 or $2 million per year by running this simulation. And second one will be cracking, and this was one of our earlier case studies, and it also is following on what has been done at a much earlier time, and which look into using neural network to predict crack formation in welding, right? As we know, this kind of cracking is also, we said it's has a very complex phenomena, and this will depend on processing parameters, materials properties, and the mechanical factors. There have been many models actually to describe the cracking or solidification cracking, and using very different assumptions. And so far, probably we do not have such a mechanism which can be applied to different type of cracking yet. Right? So this probably gave us probably a good starting point to look into multiple variables, and with non-linear correlation looking into it, right? So this is our workload. Start with data and move on to AI, ML tools, and you need to choose which tool do you want to use. For example, if you use neural network, and you'd probably look into what is the weighting factor, what the bias will be, and what the transfer functions, what would you like to do, and you make it able to get the result you want. And then you also look into optimization tools and how to optimize those parameters by using different variable methods, such as a genetic algorithm, autoencoder, this different tools to look into, essentially to find what is the best tool, and we can be used for this case study. The data set is pretty small. We said it's a small data set, and look into 784 data, which we searched in the public domain by checking papers or checking reports, websites. So essentially, and we got 21 inputs and one output with crack length, total crack length, right? You can compare with shallow or deep neural network, and to see what effect will be. And also we use kind of optimization tools such as solution RBM restricted Boltzmann mechanism, and together with a SAC autoencoder, and to solve this one, problem, and mainly because of a small data set issue. And then you can do the validation and then check the accuracy or depth of neural network. You can see different layers, so 1 layer, 2 layer, 3 layer, and for us, probably 4 layer will be sufficient. But this really depends on your case or on your quality of your data. And this is one validation we did, and we know in those 2 steers, and 304 is much a better steel which can resist the cracking, while 310S is much more prone. And then this prediction gave us the confidence, they probably are doing the right thing, we probably got right variables. And then you can move on to do further studies, do something we cannot do before, right? And then here we try to compare those 3 different types of steels, 304, showing the red color in this diagram, and a green one, which represents 305, and the blue one, 308. And then by manipulating this data or interpret different ways, and you can look at, for example, look at effect of different combination of different elements into it, right? And this will be something new, and it will be very expensive to do experimental studies. I think if you want to find more of this study, we got published a paper in Materials and Design in last year, right? So now we move on. Second one will be very quick one to do a prediction of mechanical property using industrial data, right? Or data from industry. That from industry is very different that from academic fields, and they have a real big data, millions of data, and let you to explore. Here we want to predict mechanical property, I guess chemistry and processing wise. Look into chemistry can have very different elements into it, and then together with processing variables. Right? Again, you should be able to do the training and the testing. And what we found probably for some of the properties that have better accuracy than others, right? So since then we found from this kind of industrial data one, and then we found probably a difficult part is quality of data. They have large, big data, but we are still not sure whether we can capture the key data. So since we learned, probably we should ask what question which is suitable for AI, or do we have enough data? And then can we determine the key features, right? Which ones are key variables? And this probably lead metallurgical material science to help us to do it. And then we probably, you can also compare with the statistic analysis first. We also need to look into different technology, different methods. The method you use probably may not be the optimum one or may not be the best one. You always need to compare with them and to choose or develop a suitable models which can be the best fit to predict the properties or phenomena you want to do, right? I probably to skip over this diagram. This is our certification structure. This is looking to single crystal structures, mainly to correlate this grain orientation with processing variables, right? We got paper just accepted in ACTA if you want to, they have more information in there. But essentially, what I can tell you, it is this diagram, right? Showing this diagram for dendritic core detection. So this algorithm, if you use the microscope, and we should be able to automatically, within less than 1 minute time, we can quickly to identify the primary spacing, the patterns, and also may look into the isosomal effect as well, right? But this is technique now we collaborating with Rolls-Royce, and it will be taken forward by them to do the actually industrial scale analysis of their data. Right. We'll skip this one. I'll do the final one, and then we said we are using AI for kind of a wedding project, and this is the EU project. We're partner of it, right? Essentially, this is we had a visible and transparent digital B2B online platform, right? It connects users and with the equipment consumable manufacturer, supplier, distributor, and technology service providers. And then using knowledge-based tools, and it uses AI or machine learning to do technical side and also to do the marketing side as well, right? It also has blockchain technology and smart contractor, and then multi-physics simulation and system simulation as well, right? So this is, you see, this links the supplier with the demand, right? And also take into account these kind of facilities and take into account the services linked by this blockchain or technology, and then supported by materials-based kind of simulation, and then to build such a platform which facilitates industrial networking and automation system. And it is aimed at plug and play or plug and produce kind of a level, right? This is my second last slide. Essentially, we said that we are working together. You see those AI in materials science or still making has been done probably in the last few years' time. But those activities probably is not very well organized. Each one we're doing its own part, and we'll probably need a kind of platform for us to have coordinated activities. We are preparing kind of proposals to ISC Industry Strategy Challenge Funds in the area of manufacturing made smart. We aim to build a kind of research center. We start from a primary manufacturing process, and followed by this downstream process, including casting, welding, forging, and additive manufacturing to the final components in terms of application in different industrial sectors, aerospace and then automotive and then gas and oil sectors. So, so we would like to probably take this opportunity if you have ideas, and then you're welcome to get contact with us, and we're happy to work together with you, right? Finally, I would like to acknowledge those funding bodies and also my colleagues, and then in particular, Andrew Densmore, and he was actually director of Tata Steel Research. Now he's industrial liaison in my team. And also we have Shinnapad, he will talk later on, next week. We have Jun Li, Hui Huidong, and So Feng, and also PhD student in my team. So thank you, everyone. Right. This essentially is my talk. Thank you for listening. I think we'll leave the question and answers to the end. Now I would like to invite Professor and Sir Hari Bhattacharya to present. Hari, are you ready?
Yes, I'm ready.
Right.
So hopefully you can see my screen.
Yes.
Yeah. So first of all, thank you very much indeed to everyone who's attending, and also all the wonderful people who have organized this. I'm going to explain in about half an hour how to apply so-called artificial intelligence into material science problems. And I'm only going to use two examples. Hongbia Dong has already given us enough to think about in that respect. Now, I deliberately put the title of this talk as Empirical Learning in Material Science, with the emphasis on empirical, because this is purely a mathematical technique, and there are many different names used for this. For example, data-centric engineering, machine learning, artificial intelligence. And what I want to do today is to remove the mystery behind this method. And if you want much more detail, then you'll find it on this website. Now, the picture over there shows a remarkable component which goes into steam power driven turbines for electricity production. And it is so beautiful that it gives a huge efficiency in converting steam energy into electricity. And it will operate for something like 40 years at steam temperatures of something like 600 degrees centigrade and impressive stresses without failure. Okay, so how do we design this? Well, before I go into that, I want to show you the difference between ordinary science and the sort of methods that we use in material science and engineering to actually get to the technological goal. So in ordinary science, you might take a problem, simplify it until you have a mathematical theory for the simplified version, and then you validate the simplified problem. And at that point, you've actually lost all connection with technology because you've ignored the real complexity of the problem. So, if you ask, for example, someone to do a first principles calculation on steels, they will be able to calculate the modulus, but nothing much more than that. Modeling is, my definition of modeling is slightly different. That first of all, we deal with a complex problem without changing the level of complexity. That means we identify all the relevant problems by discussion with engineers and everyone involved in the proposed component. We assemble and develop physical principles. We combine physical and empirical methods, all the tools that we have, And we do not actually give an answer without talking about the uncertainties, because we don't know everything and there are no models in the whole world which can cope with the sort of problems that I'm going to describe. And then, validation really means that you have to make a prediction, and a prediction is only useful if it is against unseen and unforeseen circumstances. So our goal is not to simplify the problem, but to address it at the level of complexity that exists. I'll give you some very simple examples. Here, here are some elementary mechanical properties which are absolutely essential before you put something into service. So we have the toughness in its various forms, we have fatigue, and we have tensile properties, corrosion. If I gave this with every single variable that's involved in controlling these properties to anybody in the whole world, they could not predict a single one of these properties, not even the tensile stress strain curve. Okay? So we have a very big hole in our methods of connecting structure. As you know, we examine structure at every resolution, but we have no method of connecting the structure to actual complex properties which you need before you actually put a component into service. Of course, we can test these, but that isn't the goal. We want to actually try and make a prediction so that we cut the time down from concept to actual production. And as Hongbia pointed out, machine learning techniques are just one part of a whole set of tools that we have. So we have the electron theories. If I want to calculate the modulus of iron in its diamond structure, I can do that using first principles calculations. Molecular dynamics deals with many more atoms, but is a bit more empirical than electron theory. Thermodynamics deals with huge quantities, but it deals with just the equilibrium state. Then we have irreversible thermodynamics, which is between kinetic theory and thermodynamics, and it deals with steady state processes. And kinetics is the dirtiest of subjects because it's incredibly difficult to predict. And the basic reason is that you need a very good idea of interfacial energies and number densities, neither of which can be predicted in a real material which contains 20 different elements and impurities and so forth. And of course, finite element works extremely well in working out the distribution of stresses, temperatures, etc. in complexly loaded components. Material science comes into the fore when you can link structure with properties and give some estimate of uncertainties. And all of these techniques are described in this little thin book, which is not very big. So you can see it's not a very big book, but it contains enough information for you to get on with the technique. Okay, so I was very careful to explain that we do not want to simplify the problem, right? We want to deal with it at the level of complexity that exists. So in the next slide, I'm showing you a plot of x versus y versus x, two variables. And you've got a set of points over there which look fairly random. So you might think there is no correlation between these data. And that's because, I'm ignoring two variables. One is the z-axis, which is pointing out of the plane of your screen. And the second one is time. If I introduce both of those, you see that the picture immediately becomes clear. Okay, just by looking at this, what this is, okay? So ignoring variables might help you to publish a paper, but it doesn't actually solve the problem that you're looking at. So as Hongbia pointed out, we can deal actually using these methods with 1,000 variables without any real new concept in the method of modeling. So very often we use methods which are empirical, and we've been using these methods for decades and decades. So if I want to, for example, work out the strength as a function of the chemical composition, you'll find many equations like this, which are basically linear regression equations. There's no justification really for making this linear. So you might say, that you should be multiplying carbon by manganese. But again, there's no justification for this. And if you have a bad dream, then you might write an equation like this, where the strength is the sine of the carbon concentration and a hyperbolic tangent of the manganese concentration. So what I'm trying to emphasize is when we are dealing with an empirical problem, we don't know what function really represents the problem. Okay, we assume it's linear because we are, we think of the simplest, but there's nothing in nature to say the problem should be simple. So we need to break away from this, okay? Break away from this kind of thinking and get a method which actually discovers the function. So the solution is, first of all, we must have, not necessarily, but we must have the ability to derive nonlinear functions without actually explaining to the method what the function should be. We want to deal with very large numbers of variables, and uncertainties are a big part of the problem. Okay, so I will come back to that. And we need data. We need database from past experience. Okay, so how do we do this? Well, this is a neural network representation of linear regression, right? And I'll explain. So here we have our inputs, which is the carbon, the yield strength, and the phosphorus concentration, and we want to predict the toughness. So what we do is we multiply the carbon by a random number, which we'll call a weight, multiply the yield strength by a random number, another weight, and phosphorus by another weight. We add them all up, and we get an estimate of toughness, which is not going to be correct, because we've simply multiplied the inputs by a random number. So what we've got to do is go back and compare with the database to see how good that prediction is, and adjust the weights until you get some sort of convergence between your prediction and your measurement from past experience. Okay? So this is a neural network representation of linear regression. The bit in the middle here is what we call the hidden unit, where the addition and other functions are done, which I'll come to later. Now, I want to break this linear bit where we simply add things. So instead of adding, I will take my carbon concentration, multiply it by a weight, and put it into a hyperbolic tangent. The reason is that hyperbolic tangent is a very flexible function. So in some regions, it can be completely linear. In other regions, it can be nonlinear, depending on the weights that are fitted to it. And one hyperbolic tangent may not be enough. So you can use a series of hyperbolic tangents, in this case 2, to make the function more flexible. So what we've done in going from here to here is we've introduced 2 hidden units in our neural network. So here I'm multiplying carbon by a weight and taking a hyperbolic tangent. I'm multiplying carbon by another weight and taking another hyperbolic tangent. And by that, I can make the function much more flexible. Now, many people who don't understand the method will call these methods black box methods, okay? And that's simply because they do not understand it. The whole process that I've described can be expressed as a single equation. And I can have any number of hidden units. So what Hongbia, hidden units and layers here of hidden units. What Hongbia said about a simple neural network and a deep learning neural network. So the equation describing this is very simple. No matter how many hidden units I have, that this is my output, and this is my set of inputs. These are the weights, the hyperbolic tangents. These terms are like the constants that we have in our regression equations. So this is a highly nonlinear function and deals with as many variables as you like, as long as you have the data to train the method on. Training is just another word for fitting. And just to illustrate to you how powerful this can be, I'm just going to show you here 2 variables, x and y. and we are plotting the output Z, and we are just using 4 hyperbolic tangents, and by varying the coefficients, you can see that you can make this surface sing and dance. You know, it is an extremely flexible surface. Okay, so no matter how complex your data are, you can actually find a function which will capture their behavior. Okay, so I said, no matter how the complex data are, you will find a function which fits them. So there comes the first problem with this kind of analysis. This is very, very powerful, and I can make the function pass through every single point here. But if you make it sufficiently complex, then you can pass through every single point. And then you're faced with the question that, look, is this the correct function, or is this the correct function, the linear function? And most people would argue it's the linear function because we have some error bars there. But that isn't really a good way of testing which one is justified. It could very well be that this is the correct function, the more complicated function than the linear function. So how do we do this? Well, it's actually not very difficult. So you have your data set, and you divide it at random into 2 parts. Okay? You use only one part for creating the model, and use the other part for testing how it behaves with unseen data. That's the important thing, okay? Unseen data. So if I use unseen data and I get a prediction here, then clearly this function is the correct one, okay? As opposed to this. So here is an illustration. The black data are the data you would use for training, for creating the model, and the white data here for testing the model on unseen data. Now you can see that the linear function here is not really capturing the complexity of the data. It's too simple. This is a function which is more complicated and manages to pass through every single data on which it was trained, but it behaves badly on unseen data. So this model is too complicated. So if I plot the error here against the complexity of the model, if the model is too simple, I will get a large training error and a large testing error. That testing is against unseen data. If the model is too complex, we will get a very small training error, but a very large testing error. So here you can see this point is far away from here, and the further I go, I will get a bigger errors. At some level of complexity of your model, you will find that the test error goes through a minimum. And here is an example where you predict reasonably well both the training data and the unseen data. So this is how you would fix the complexity of your model, because as I said to you, the machine learning techniques give you extremely flexible functions. So you can just force them to pass through every point, but you might be modeling noise in that process. Okay? So this gives you a clear way of fixing the complexity of the model. So you then fix the complexity and optimize the model further. There is a further problem. And that is, look, if I have a set of data which are completely accurate, there is no error whatsoever. So here we have the integers 2, 4, 6, 8. And I ask you to predict the next 2, then I'm sure that you will predict it's 10 and 12, okay? And you predict them precisely on this linear function. But I have another function which will do the same thing. Okay, this function at the bottom, if I put the number 2 in here, it will predict exactly 4. If I put 4, it will predict exactly 6. And if I put 6, it will predict exactly 8. But if I put 8, it will predict exactly 8.91, and so on. So these are 2 functions which precisely fit your experimental data. Okay, so here is an illustration of the same thing, that the black line here is the linear prediction. This is the only region where we have data. and both models exactly predict the same experimental data, but they behave completely different outside of the known domain. So this is a problem that cannot be solved. Okay. However, we need to take advantage of this. The uncertainty that we get when we repeat an experiment is called a noise, because when we do two tensile tests and you get different results, that means that you haven't controlled something. For example, the dimensions of the specimen or the shape of the specimen. Okay? So that is noise, and we are all familiar with noise. This is completely different. There is absolutely no noise in the data, and yet we have an error here. Okay? And this error is very important. It's a new kind of an error, which is a modeling uncertainty. So we have here two models which behave different, and here the modeling uncertainty is very large, here it is smaller, and here it is even smaller. Okay? Now this is extremely interesting because it tells you when you are working in a region where there is no knowledge. Okay? That is exactly where we want to work, all right? Because we want to create new things. So if you are working in this domain, then basically you're wasting your time because we already have the knowledge. Now, of course, in this example, it's quite simple to point that out, but when you're dealing with 1,000 variables, if you get a very large modeling uncertainty, that's the place where you want to investigate, okay? So there are two errors in all the slides that I will show you subsequently. One is the noise, and the second is the modeling uncertainty. It doesn't mean that our prediction is wrong in this region. It means we need to be careful. We need to think about the prediction and what could have produced this large uncertainty. And this is another way of illustrating the same thing. In the domain where we have knowledge, you know, all these models are fairly good representations of the data, but the modeling uncertainty is larger when you're making predictions in the input domain where there is very little knowledge. Okay? So I think this removes the danger of extrapolation, because you get a warning that, look, you're working in a region where we don't have much knowledge. Do you have any other physical ideas which might say, yes, even though the modeling uncertainty is right, this is likely to be correct. Okay? So you need to bring in all your other knowledge and experience to work in this domain, which is actually where we are creating new things. Now, going back to the talk that Paul gave at the beginning, where he was talking about sustainability, I actually happen to have a slide to show how to solve that problem, okay? So, you know, the easiest thing is if all of you stopped eating meat, that would solve the problem completely, all right? In a very rapid period of time. But it's very hard to persuade you guys to stop eating meat. So let's try some other thing. So this is going back to my power station, and conventional power stations work in a region where you're working with steam, which condenses into water and so forth. So the temperatures are of the order of maximum 630 degrees centigrade steam temperature. Now, what we would like to do is to go in this ultra supercritical temperature range, where the steam temperature can be greater than 700 degrees centigrade and a pressure of about 22 megapascals, where there's no difference between the vapor phase and the liquid phase. So they basically have merged as a single phase. And that has advantages in efficiency. And the fact that we want to go to much higher temperatures also increases the thermodynamic efficiency, because the thermodynamic efficiency depends on the difference between the highest operating temperature of the cycle and the lowest operating temperature of the cycle. Okay, so I'll begin by saying that there is no steel which can survive a temperature of 750 degrees steam temperature, 100 megapascals stress, and a 40-year lifetime. Huge amount of effort has gone into this to try and push the limits of ferritic steels to 650 degrees, and they haven't succeeded. The maximum we can get to is 630 degrees. Now, we could use austenitic stainless steels. The problem is that the thermal expansion coefficient of austenite is much bigger than ferrite, and therefore you get failure from thermal fatigue because the temperatures are not constant, okay? So we need another alloy system, okay? And of course, we can cope with higher temperatures in it. As Hong Biao knows, in the jet engine, you know, the highest operating temperature in here is in excess of 1400 degrees centigrade, which is higher than the melting temperature of the nickel-based superalloy that you put into that region. So it's protected by various coatings and cooling channels. Unfortunately, these alloys are incredibly expensive compared with the scale of engineering required in a power plant, right? So they contain exotic elements and so forth. So we need to down engineer these alloys because we don't need to go to 1400 degrees centigrade. We can cope with 750 degrees centigrade. So we took on a project to design a nickel alloy, which would be extremely cheap. It's still 3 times more expensive than steel, but far, far cheaper than aerospace alloys. And you could make it in large quantities, right? And fabricate it, etc. And you know, if you look over here, it contains 5% of iron. Iron is not a good thing in nickel-based superalloys, but by allowing it to be there, you can use scrap material to make this alloy. Similarly, when you make a very large component, the problems of chemical segregation become much more prominent. So we used methods of kinetics and thermodynamics to ensure that if there is chemical segregation, it could be more or less homogenized during the fabrication procedure. But as I said to you, ultimately what we need is properties. So this is completely theoretically designed, right? And the property part was designed by taking the vast amount of public domain data that we have on nickel-based superalloys and doing machine learning. So this is the alloy microstructure where you have these gamma prime particles, but the volume fraction here is only about 20%, whereas in an aerospace alloy, it would be of the order of 70% in the blades. So it's a very simple alloy composition, and the structure is as we would like it. And look, the data there that you see, the data points, those were not measured at the time that these predictions were made using our neural network model. So this curve was actually predicted, and these are our modeling uncertainties. And this is the strength as a function of temperature. Now, the reason why the strength persists to high temperatures is because in these precipitates, the mechanism of slip operates, which gets more and more difficult as you go to higher temperatures. Okay, so here, yield strength properly predicted. Creep strength is really important, right? And you can see that our modeling uncertainty is very large here. And this is the predicted curve. And we are not worried about the fact that the modeling uncertainty is large because other metallurgical data, for example, the microstructure and so forth, tell us that this should be able to resist a stress of 100 megapascals at 100,000 hours. That's the typical 100,000 hours is more than a year, right? So you can't do these experiments and then say, okay, you have to wait for 5 years before we give you all the data. So this is predicted, and these are experimental data, and these tests are ongoing, but actually this is quite old work. So we have really long-term creep data on this. And we named this alloy FT750DC. FT is the postdoctoral research assistant, Frank Toncray, who did the work. 750 for 750 degrees C steam temperature. And I bet you can't guess what DC is. DC means it's dirt cheap, extremely cheap alloy, because we removed all the expensive components of nickel-based superalloys. Now, ordinarily, to develop an alloy like this would have taken very long. much longer than, people can wait. So this whole thing took approximately 2.5 years to do. So these techniques are very powerful in predicting structure property relationships. So you can even have a neural network where you feed in the structure as opposed to other parameters like composition and heat treatment. Now, fatigue is a very, very important problem. And the whole reason why Boeing became a prominent company is because we had the comet disasters in Britain, where we had these fatigue cracks forming at stress concentrations on these windows and the rivets near the windows. So it put back, this was the first jet engine for civil jet engine ever, okay? And you could fly above the weather and so forth and so on. But 3 of them crashed, and the reason was this fatigue failure, and that established the standards by which aircraft should be produced. So you have an aircraft on the ground, which is constantly being pressurized, depressurized, and simulated flying before you put aircraft into the air. And even when you put aircraft into the air, you have the ground test aircraft still going to predict long-term problem. Okay? So I think, I don't have the proof, but I believe that more than 95% of engineering failures are due to fatigue failure. I don't have a reference, I mean. So we decided to create a fatigue model. And there are huge quantities of data available on fatigue crack growth propagation. So we took all these data and we created a neural network model which includes the variables you see at the bottom. So this is a fatigue crack growth model. And the vertical scale is simply our perceived importance of these variables, right? So the data are all on steels, a vast range of compositions, test parameters, etc. And I'm only showing you a few slides. So the error bars here represent our calculations, and the points are unseen data. Okay, so this is the normal way of plotting crack growth rate, where you have a stress intensity range here and a crack growth rate, and it's logarithmic because that's the relationship between the crack growth rate and the stress intensity range. So you can see it predicts really quite well over many orders of magnitude of crack growth rate. And this steel, for which you see the data, was not included in the database. Now, I want to show you something really quite astonishing. Okay, I explained to you that this model was created entirely based on steels. However, if you look at these variables, they are exactly the same variables that you would use for any other material. So the model doesn't know that this is specific to steel. Okay? Apart from the magnitudes of the various parameters, it doesn't know that it's produced on the basis of steels. So we should be able to apply it to anything. And we tried that, and you can see really quite remarkable prediction of fatigue crack growth rate in nickel alloys, even though the database doesn't contain a single nickel alloy. And then we tried aluminum alloys, titanium alloys, and you can see that if you design your model appropriately, it can be of generic value. Okay, so I'm going to stop because I'm running out of time now with this last slide. So I want you to decide whether the method is intelligent or not. But I was talking to a biologist who was working on very simple forms of life. And how does she define intelligence? This is a well-established method in biology, that the first component is that you must have episodic memory. That means you must have retained in your brain something that you've encountered in the past. So for example, if this very simple creature sees another one of its kind, but doesn't remember that it has seen, then that's not episodic memory. Episodic memory would mean that you can recall information. Now, your recollection may not be the same as another person, Okay, that's because of the complexity of our mind, but nevertheless, you can recall. The second thing is that by recalling that information, you should be able to plan the future. Okay? And you should be able to reason with those data and plan the future. Now, I don't think that machine learning is really anywhere near an intelligent method, okay? And I'll tell you a joke. I was going to the US and the immigration officer asked me, what am I going there for? So I explained that I'm going there to give a talk on neural networks, and I thought I should explain that it works a little bit like the brain. It doesn't, okay? I said it works a little bit like the brain. So he said to me, I wish my boss had a neural network, okay? So I will stop there, and there's a reference there where you can read a lot more about these techniques. Thank you very much.
Thank you, Harry. And your exploration on this neural network is very intuitive. And then to describe way of how to apply the weighting factor bias, and then to do this, to correlate is a complex kind of relationship with this kind of linear equations. Yes. Yeah.
You saw how well it fitted with your talk and with Paul's without any planning, okay?
Yeah, yeah. One thing, in the end, you mentioned this kind of episodic memory. Yeah. And I was wondering, in this kind of memory, if you want to do planning, and you need to have some kind of operation inside. Yeah, you have memory. You want to
yeah. So in the case of these very simple creatures that my colleague was studying, you offer food at a certain location. Now, if you don't have episodic memory, and you basically look at random for that location.
Right. Right. Okay. We may have a question come up. Yeah.
Right. So I think we are far, far behind in talking about intelligence, and the terms like neural and so on make the subject sexy, but it's actually just mathematical. We fully understand it, right? And if you run the neural network, again, it will give exactly the same answer.
Yeah, it's sort of data fitting. And then, but yeah, I think this is the way we learn things. You try, you got enough knowledge, and then you can try to use simple way to interpret what predict after this range. Yes.
Right.
Yeah. One thing we have something we can share with others. We did some mechanic property prediction, look into tensile strengths, elongation, and then yield strengths, and also this fracture toughness data. And the data set is quite large. We took into 10 million kind of data individual measurement points. And then those data were taken from same sample, real sample, because they accumulated over years' time. And then we in the end, what we found probably for this yield strength, tensile strength, elongation, we have much better accuracy, looking to 98%. But fracture toughness ends up around, we tried our best, we could probably get to 90%.
And once you have trained the network, it runs in milliseconds. The training and creation of the network might take 2.5 years if you do it properly. But once you have it, I have a model over here on my Android phone, which is quite old, for predicting transformation temperatures. Okay? So you don't need heavy power once you've actually created the model.
Good. Okay. And then we will ask Shunapa and Jenny. Have you seen any questions so far?
There's a question actually to you, Hong and Harry. Is there any case in the real world to use AI to design alloy that is practically used in industrial products? So the keyword is practically used in industrial products. It's a lot of question coming up now, I can say. People typing, but yeah, the first question to you, both of you, is this.
Yes, there are many examples. So for example, Nippon Steel wanted to design a welding alloy for fire resistant. Yeah. And one of my former students who returned to Nippon Steel did that in a matter of a day, and it worked. Using the models that we had created. Yeah. So you know, there's absolutely no doubt whatsoever. I have many examples which you'll find on my website, where you actually create real materials which are used by industry using these methods.
And then probably adding on and then using this machine AI thing. Another thing is it's quick solution or quick answer, and it's important for the industry. For example, if you look at this modern industry, probably many of them already have this kind of online monitoring system, the very different sensors to measure temperature, measure chemical concentration, measure pressures, right? And then, as I mentioned, we quickly talked about it in this glass forming industry, and then you can do simulation first, but those simulations will be validated against experimental results. So you can create this kind of high dimensional space, and with grid of data embedded into this space, into this space. So when it's operation, and then if you know your current status, and then you can quickly through data processing, through available data in this high dimension space, to predict what will happen in next time step and what can happen in downstream process. So this is
hello.
Yeah.
To move on from online monitoring, using the data, current data, to predict the future status.
And in general, you wouldn't just use machine learning, you would use all the other tools at the same time and experience,
of course,
so forth.
Yeah.
So they cannot be used. They cannot be used blindly.
Yeah. Last year I visited one of this kind of modern steel making factory. They have wisdom center, and then when we went to the hall and wisdom center hall, it's very I was very impressed. And then they have thousands of monitors with different kind of display things.
Right.
Sure.
Yeah. And if this goes wrong, for example, this we got a cracking occur in casting, can the machine tell you? Or
yes,
it's decision? No, it's people make decision or machine make decision. And also we got make the decision. Yes. Yeah.
Sure. I mean, we have got quite a lot of questions now, so I'll try to read the question for both of you. Question to Professor Bhattacharya. What is the best way to model the relationship between alloy microstructure and properties? I think this is quite. What is the best way to model the relationship between alloy microstructure and properties?
Yeah. So I think it depends on how complicated the problem is. Okay.
Yes.
So you could, for example, you could decide that, look, I'm going to introduce this number density of precipitates, and then use some dislocation theory and estimate how much of an increase in strength you're going to get. But there's no way that you could predict elongation, for example. So it really depends on the basket of properties that you need for the alloy to be successful. So if you look at high entropy alloys, you see hundreds of papers published with a measurement of a small sample in compression. That is silly. Normally, to produce a component, you have to have a whole basket of properties that need to be optimized. But I think when it comes to complex properties, there is actually no method other than machine learning. There is absolutely no method to predict creep rupture life or fracture toughness. You can measure all these quantities, but there is absolutely no method of predicting them. I would challenge anybody in the whole world.
Yes. So I think actually I have my own question to you. In order to get the success of the AI to metallurgy and materials, do we have to move to stochastic kind of mathematics in order to deal with those kind of a large ensemble from the scatter in the property you just said? For example, we concentrate on the small specimen rather than a large chunk of I mean test pieces, for example. What do you see the future of this research?
But I think that's a very good point. You know, the variability. All right.
Yeah.
The good thing is that many of the data that we use for
Yes.
machine learning
Yes.
come from actual industry. That means they are
Indeed.
actually making. So they have large numbers of data.
Yes.
Which you know, when you repeat the test, it's not the same. So there are statutory requirements for critical components on how many times you repeat the test and so forth.
Yeah.
And how many of these should fall outside this. So they do all the tests. So if you have
Indeed.
access to the data, that's perfect. Yeah. Well, one problem, of course, is that people don't report all the variables, and they don't.
This is a problem.
They don't report unsuccessful experiments.
Yeah, this is important as well for us. But anyway, let's move on to the question. There's a lot, and now this question is go to Professor Dong and Harry. Can the input variable of the artificial neural network be dependent? Is the noise in experimental data has the limit for the prediction accuracy?
Right, I think the input data is important, and then first one we'll say we'll see probably a key data. What are the key data in there? And the second one, probably you need have enough data. You may have problems if you do not have enough data. But for us, and if you look at the quality of our data, they usually have strong correlations. Compare another data in commercial sector. You know, for example, if you go to shopping, the article was shopping, that's quite a random one. For us, you know, we all probably already know what are the processing variable and will be influence certain aspect of performance during manufacturing. So the data is important. The data is the key for the accuracy of your prediction. But you need to have certain knowledge and to how to interpret your prediction with the input of the data. So this was we need to have materials knowledge or metallurgical knowledge to interpret them. For probably a small set of data, this even become more important. Probably for if you have bigger data, it may probably be able to reveal it. If data is not enough, and this can be embedded in the noise.
Sure.
Yeah, and you know, the modeling uncertainty that I talked about, that will tell you whether you have enough data or not. Yeah, so at the beginning, you don't need to worry too much about whether you have enough data or not. If you're modeling uncertainty in the region that you're interested in is large, then you don't have enough data. And interactions between variables are automatically captured. So if you do a prediction of strength versus carbon concentration in one region of the domain, it'll be different in another region because the magnitude is different.
And also in this, if you use a neural network, you may have other tools and to help you to optimize them. And what we did for we call small set of data simulation, and you may have choose right tool to optimizing data as well. This will help you to increase the accuracy. Yeah. Jenny, have you any questions so far?
Sorry.
Jenny,
sorry, I do the standard trick of not unmuting myself. So I think as there are so many questions that have come up, it seems only fair to ask one of those. So there's a question that regards simulation data sets from physical-based models and whether it's actually useful to be able to combine simulation data with machine learning.
In my talk, I refer to this industrial kind of data set. As I mentioned to you, in industry and that data, probably the quality of spread is very different with the data normally we have in academic field. When we do our research, I always want to do something different. So our data is normally more spread out. And in industry, if you look at industrial operations, they're operating at one point. And they repeat this millions of times. And also, if you look at quality of data, sometimes it's not as we wished. For example, if we want to control the carbon concentration, right? And then say if we want to control carbon concentration at 0.2%. So ideally, we will have data around 0.2. You will have 0.19, 0.18, and then 0.21, 0.22. This is the data we probably want to have. But in industry, what data you will get is 0.1 and 0.2, and then lower down 0.1, and then further up with 0.3. You probably are missing some kind of we say distribution, a good distribution of data. We don't have it. So simulation will give you the way to back this up. But simulation need to be validated. And if you look process-wise, and then you need to spread them out, and then which probably you cannot do in industry. So we need to have simulation on, and also simulation will generate probably lots of spread data which have good distribution, and then rather compare with industry data, probably they focus on one operating point. So it's complementary, and then I think simulation should play a very big role to look into the trend, to spread the regions.
So for example, first principles calculations are very computationally intensive. So if you have to do that for a variety of structures, say, then you may not do it for all the structures that you're interested in, but do it for a few and then use machine learning to interpolate between those. That's quite common.
Yeah.
Yeah. Great. I think we have another.
Paul is also ask questions. Paul.
Yeah, I think there's some a person called Shi. He asked Professor Madesia, and he said thanks for your great presentation. And he asked, he's wondering how we can use or determine or to reduce the error based on the empirical relation.
Yeah. So as I said to you, there are two kinds of errors. One is the noise. That means when you repeat the experiment, you haven't controlled some variable, and therefore you get a slightly different result. That's straightforward to control. You either identify all the variables that you need to get a precise measurement, okay?
Yeah.
Or to the level of precision you're happy with. But the second kind of error, which is the modeling uncertainty,
yeah,
that you can only solve by making first a prediction and then doing an experiment in that domain to see whether, and you know, the great thing about neural networks is once you generate new data, genuinely new data in regions where there's a lot of uncertainty, you can redo the network.
Sure.
And it has learned from that process.
Yes. Of course. So we will, Jenny, probably move on to the next question.
Yeah, so there's a question here from Sam Perry, who asks, and this is to Harry, and it's really asking about the current limitations within material science for actually producing accurate neural networks, and whether materials researchers should actually change the data they include in future publications. So maybe including more microstructural images, complete data sets, or actually including failed tests.
Yeah, so the really good thing is that some years ago, the UK government asked all researchers to archive the data that go along with the publication. So, you know, if you publish a paper, you probably have gigabytes of data which are not in there, which you put on the university's archive, not on your own web page. And that, I think, is a very positive step forward. You know, if I wanted to know what Darwin did or Newton did on a particular day, I can find that information. But if I look at your paper from 10 years ago, I cannot find that information. That cannot be right. So archiving of data, which would include any data, including failed experiments, etc., is now really quite common, and all universities in the UK have created these archives, most of which are open access.
Okay. We have the next question is from Bolshan. He said that thanks very much for your very interesting talk, Harry. For your universal fatigue crack model, would that be similar to the Paris law? First question. Dealing with the fatigue crack growth seem to be less challenging compared to the fatigue crack initiation. If you try to extend a fatigue crack initiation model based on steel to other materials, it would be most likely fail. Is my understanding correct? By the way, I was first bought into neural network field, but your creep strain prediction paper, again, one of the remaining challenge is how we can use the neural network to predict something we are not 100% sure about, the mechanism such as creep fatigue.
Yeah. So
it's quite long, yeah.
I think the neural network cannot capture anything that is not in the data. For example, if I create a creep model, it will not be able to predict for creep fatigue. Yeah. But going back to the first part of the question, initiation. So there is something called the threshold stress intensity range,
yes,
which the model predicts fairly well. What it doesn't do is, if you take a completely smooth specimen,
yes,
right, and you want to predict its fatigue failure in a rotating bending test, and that is mostly controlled by initiation, you can't do that. So you'd have to create a model for that sort of an application. But most engineering materials contain defects already.
Of course.
Okay, they won't be smooth. The reason for doing smooth tests is when you're dealing with smooth objects like shafts, for example, and you want to understand the role of stress concentration. So I think you have to deal with the properties separately, because there are different mechanisms, the initiation and the failure. So engineering materials will contain defects which will already be fatigue crack nuclei. It's just a question of how long it takes them to get to a critical size. And yes, of course, the model that I was talking about is the Paris law.
Okay. Is that extended to other material as well? Is that another question?
I think Paris law is generic.
Sure. Okay. I think there's another question probably relevant to mine, but they probably asked both of you as well. Is it possible to predict residual stress of AM product, which is additive manufacturing, with machine learning? I think this is one remaining question.
Would you like to answer it?
Probably Harry. I mean,
I don't know enough about this.
Okay. Yeah, but I don't know why this is question coming up. But
no, but additive manufacturing is a big business now. So
yes, of course.
I suppose that people are not publishing data, right?
Yeah, that probably is the main.
Yeah, that is the main. Even the model,
yeah,
the physical based model, it's a number of physical based model in terms of thermal fluid flow that they use in the research at the moment. They're not published anymore, but I publish. So if you are interested in the additive things, probably next week you come to listen again. Are there any questions left, Jenny?
Yeah. So there's a question from Andrew Dunsmore who says that neural networks have been around for 30 years, but we're still mechanically testing steels, probably because of the non-homogeneous nature of the steel processing, etc. So do you think we'll ever get to the point of zero destructive testing? And what will it take to get there?
So Hongbeo Dong in his presentation gave this steel plant slide where neural networks exist, and you can actually buy a model from Siemens for online control with feedback, so that the final steel has a much lower scattering properties. Okay, so the model senses, that certain variables have changed, so it will make adjustments, and therefore you get reliable properties in the end product with much reduced scatter. That's one example. The second example is that the testing for hardenability is completely eliminated. You can predict now the Jomini N curve without actually doing measurements. So it depends also on, so in the university, we deal with difficult problems normally. In other words, critical components.
Yeah.
For critical components, you would, by regulation, you would have to do a certain amount of testing before.
Sure.
I also think probably we, even in the future, we still probably lead the kind of testing to validate or to gain more confidence. Because as we said, probably if you look still making process, there are so many variables, and then we may control some of them, not all of them, right? Yeah. So this still give uncertainties, and we still need to probably, it's complementary scale, and then we neural network, and then with practical testing, I think that's in this way. But we're doing much less experiment and a much quicker way. Right?
Yeah. So regard it as a tool which reduces the time scale. It doesn't solve everything.
Yeah. I think we have one last question, which is probably sum up the seminar today very good. Is this that what is the scientific point of using AI in material science? It may has some, industrial guidance significant other than scientific meaning. Do you have any comment on that?
Absolutely. So if you do not have a model to deal with complex properties, then you are predicting structure which the engineer is not in the least bit interested. Okay. So you are failing in your job of reducing the time scale for experimental work, because you will have to make an alloy, you will have to test it, and that alloy won't be representative because it's made on a small scale, and so forth and so on.
Yeah.
So that is sufficient justification, I think.
I think so, yeah. Probably this question is more like, is that more relevant to industry, the AI in material science?
Not really. So if you are working on high entropy alloys, people have used the method to narrow down the alloys which will give you a single phase.
Sure.
So even in the research, high entropy alloys are next to useless, all right? They have no application, but they produce lots of citations. So people are doing lots of research on that and competing with each other. And there is a group, several groups who have used neural networks to narrow down the composition variables.
Sure.
So it's not at all connected with industry.
Indeed.
And also scientific research sometimes quite different with industrial production, looking manufacturing. And then when we you have a developed series, probably it's generic model, and we made simplifications, and then we may miss something which can play a role. But using AI should be able to include or at least start with available data, analyze them from different angle, as we conventionally way of thinking. For example, when we look at things, we probably start from thermodynamic, kinetic, and then to microstructure, correct to the property, and then using this data analysis give us different angle, and then to look into. It can be wrong.
I think to identify the domain where you need to do an experiment, and you have 1,000 variables.
Yeah.
It's really important. Otherwise, you're just repeating what somebody has done.
So this is an area that can be new findings embedded. Has been ignored by our simplification in our theory building practice. Yeah.
Yeah. Sure. So AI is useful for both scientific and industrial uses.
Thank you all. Okay. So
thank you very much.
Thank you. Right. Thank you.
Thank you very much. Thank you very much, Harry.
And many thanks to everyone, and then for joining us and then taking part in this seminar. We probably will be making this available, this video available, but anyway, we'll discuss this in later on, right? So next seminar will be same time next Wednesday.
Of course.
Yes, and then also more than welcome to join us. Shinapati, you would like to say a couple of words about next week's seminar?
Yeah, and next seminar will be about the along the line of alloy design or process design that use that feed into AI or use the application of AI. There are 3 talks in that seminar. The first one is actually my talk, is more like physics-based model for additive manufacturing. The second talk is from Richard Curry from University of Swansea University. He will talk about the Sustain project, what is a digital manufacturing that they are working in the Sustain manufacturing hub, which is steel for steel making industry. And the last talk is from Professor Gao from Shanghai University, Jiang Gao from Shanghai University. He will talk about the big data. They use machine learning for metallurgy research. And I look forward to welcoming you next Wednesday. And thank you very much, you all. Thank you.
Thank you all.
Thank you,
Bye.
everyone.
Thank you. Thank you.
Good.
Bye.
Okay.